speed sensors or velocity sensors. There's not many of these, so it shouldn't take us very long to get through them. So we know what a sensor is now. It's a device that converts the physical stimulus into an electrical equivalent. We know we've looked at position sensors. We've looked at, they're coming up here, I need to speed this up. We've looked at position sensors, we've looked at proximity sensors, and of course now we're going to look at speed sensors. So these are the ones we're going to look at: a tooth, rotary. We're going to look at a Hall effect, magnetoresistors. We're going to look at tachometers, and we're going to look at AC tachometers. We'll look at incremental encoders and Hall effect magnetoresistive optical. Ours we actually have is actually used as a Hall effect sensor. So speed, we have I think over in, if you take the mechanics class, this is what they use. They actually have a tachometer, and you put a little piece of reflective tape on there, and then it uses I guess it would be more like a reflective. It's not actually a retroreflective. And when you shoot your beam out, it bounces back, and every time the thing rolls around, they calculate the RPM. So this is a handheld. This is a variable reluctance. This is I don't know if this is what they use now, but this is what they used years to actually edge a speedometer for your car. No, for years they actually used the cable. It was actually mechanical. So they actually ran a cable up from your transmission. They had a gear in there, and what it had offsetting magnets, and this would spin, and out here it would actually pick up and it would be working against a calibrated spring, and it would move. That was back in the old days. Now your speedometer is electronic. So all you got going to your back of your speedometer now, instead of having a cable, you're having a what? I had a Honda Shadow, 750 Shadow, that still used the cable. It had an actual cable coming up and had a gear assembly on the front wheel. Then I got my Harley, and it was electronic. And it was real funny. It got a little short circuit in it, and it was reading the wrong speed. So I got pulled over for it. I thought I wasn't going right. But this is basically what we can use. These are very, very reliable. So what we do is what determines how much EMF we induce with a magnetically. What's the thing? What do we need? Yeah. The magnetic field, right? Conductor. And we need relative motion. What do we mean by relative motion? Something's got to move. Now, what determines the amount is the strength of the magnetic field. The number of coils or loops, and then of course would be speed of the motion. So the way your alternator works in your car, it spins the magnetic field, and the stator, the stator on the outside is stationary, because we don't want to get all that current off something that's spinning, right? You understand that? Then what we can do, what your regulator is doing this. It's controlling the strength of the magnetic field. So that's why your car puts out about the same thing even though you're sitting there revving your motor, right? You understand, or you're going 30 miles an hour or 60 miles an hour, your alternator puts out pretty close to 14 volts. Well, how does it do that? Because we're changing the speed. If you ever looked at your alternator, it's connected directly to your motor. So if your motor goes faster, your alternator goes faster. If your motor goes slower, your alternator goes slower. So when you slow down or sitting at a red light, if they didn't do something, then all your lights and your radio and everything will go off, right? You understand? And then when you got up to like 60 miles an hour, everything would burn up. So what do?
That tail thing. I guess my friend, they're talking about like a new car.
It sounds like an electric car to me.
I think they call it something like that, but it turns off and turns back on. It turns back on.
A lot of golf carts do that. You ever notice that? You press on the gas, it cranks back up. No, those are gas ones. So what happens here? So what happens is you got a regulator, and what it does when you slow down, it increases the strength of the field, and when you speed up, it decreases the strength of the field. That's what the regulator on your car does. So what are we changing here? So we got metal teeth, we got a magnet, and the only thing that's very simple is we got a bunch of coils wrapped around the magnet. So we're not changing the strength of the magnetic field. We're not changing the number of conductor loops. So what we're doing is when that tooth comes around, the magnetic field concentrates, right? You understand? And then when it's in the gap, it deconcentrates. So what we're doing is changing the rate of the motion. So the field is actually doing what? I understand that. And this is very, very simple. Variable reluctance. This is also used by most cars to sense your wheel speed. Right now, just about every car has what we call anti-lock brake systems on it. So if you slam on your brake real hard, if it ever does that, it does what? If you ever go your car, and what that is your watch, your anti-lock brake system. So what it's doing is keeping up with the speed of your wheels, right? You understand, compared to the speed of your motors. And so these are very, very reliable, very rugged. So all we're doing here with these variable reluctance tachometers, we're checking speed, but it's the rate of the pulse, how fast is the pulse. So it wouldn't surprise me if this is what they're using now on your speedometer. And all they got to do is just have a gear on your transmission now, right? You understand? That when it spins, when those gears come around, it picks it up. No, this is just a magnet. There's no Hall effect here. So what happens is when this tooth comes under it, it concentrates the field, so the field goes through the tooth, and then when it goes in the gap, the magnetic field is not concentrated anymore. So what's happening is the magnetic field is fluxing around the outside of the magnet, right? You understand that? For the tooth. So every time a tooth would fly by, we'd get a little pulse out. And then this would be the gap, and then we'd get a little pulse out, and we'd get a gap, and we'd get a little pulse out, because you're concentrating the field right through a piece of metal. And that's what the magnet is seeing.
Like on that wheel there, how does the sensor determine how many loops coils there? How many times it's going?
Well, they don't. It's got to be, we would feed this into some type of circuit that would come in and take this and give us a rate, right? You understand? So on your car, we have these, we used to have no computers on our car. But now we got at least two. We have what we call an engine control computer, and then we got a body control computer. Well, which one of this would come into? So whichever one this comes into, for the tach gauge, this would probably come into the engine control computer. And it's doing what? It's doing all the counting the pulses and giving you speed, stuff like that. Yeah, so just about all these sensors give us a signal, and it's up to us what we do with it, right? Y'all understand that? In this class, we're using nothing but relays to take the output. The book calls it an interface. An interface is when you make a connection to. So it's hard for these sensors, these solid-state sensors, it's hard for them to run big loads. So one of the labs we do is we come over here and we have our sensor, and I think it's our 3-wire sensor. And then we come over here, and then we have a control relay. And then down here, we use a control relay. We use a contact on our control relay to bring in our motor starter. So the sensor itself might not run a motor starter, but a control relay. So what is a control relay? How did it get, how does it get its name? Why do we call them control relays? Well, we call the circuit, we called it a control circuit. So in control relays, the contacts never leave the control circuit. They never make it into the power circuit. So normally a control system is made out of two circuits. We have control, and then over here we have a power. And your big over here, this might run off of 26 volts DC. Over here, this might be 6,000 volts AC. Which one will kill you? 6,000 volts. 24 volts, it would be odd to get killed by 24 volts, right? It would be very unusual. So your control cabinet is usually low voltage. Everybody's got a key to this one. In fact, control cabinets are usually not locked up. We went out to Brosa and they were showing us the power cabinet, and it took 2 keys to get in this guy right here. So you had to have the technician and then plus the supervisor had to come in to get in this guy right here. This guy right here, anybody can get, right? Understand that? So there's a big difference. So if I've got a relay, if I need a relay, so how many contacts do we usually get out of these things right here?
3.
1. Normally 1. Right? Because most of them are 3 or 2 wire sensors. What if we need to control 15 different things with that sensor? Well, we use it to bring up a what? We use it for a control relay, and then the control relay would provide the contacts that we need. I think I passed it around, the one that's got like 8 sets of contacts on it. So that's determines this. So control relays, their contacts are always in the power circuit. This is what PLCs replace right here. They replace all these control relays. They don't replace these, they replace these. And 90% of a big control program, 90% is control. 90% is just determining when things happen, right? Understand that? And then eventually we need to output power or control power outside of the circuit. So it means if I got a PLC, 90% of my circuit will be a program. And the other 10% would be the big power relays out there that the PLC is. So variable reluctance, very similar, look like a lot like most of our systems. So you gotta be careful, just looking at them, don't know what type of sensor it is. A Hall effect, so we can use Hall effect. So what we do is, here's the Hall effect. Works on exactly the same principle. We have our magnet in behind the Hall effect sensor itself. So here's our magnet. Here's the Hall effect sensor. And when the teeth comes around, it concentrates the magnetic field through the Hall effect, and the Hall effect picks that up. Gives us out a series of pulses, right? You understand that? So it works a lot like a variable reluctance, but now we're adding more complexity to the sensor. Tachometers. So tachometers, all these are tachometers, by the way. These are DC tachs. So basically, these things are very simple. In fact, what I've got set up here is one thing nice about a DC motor is we can run it as a motor or we can run it as a generator. Most of your tachs use permanent. Most of your DC tachs are permanent magnet motors. So it means we don't change the strength of the magnetic field. The strength of the magnetic field is constant. And so then we got our rotor sitting in the center. And now the output of the DC tach would give us a voltage that's proportional to the speed. I don't know why I keep doing that. So I made this little thing. This would be called an MG set. We had one out at US Steel. It was on an induction heater that ran on 600 cycles per second. And all we had available out there, of course, was 60 hertz. So we had a big motor running an AC generator. So I'm running this motor, this is running as my motor, I'm running this as my generator. So I've got that flapper on there so y'all can see it turning. So a DC motor, any DC motor can be run as a generator, but we wouldn't want to change the strength of the field, so our field is constant. And here's my meter, can y'all see it? So as I increase the speed, I guess I can lay it here beside the motor. All right, somebody got my meter leads. Y'all need to get them back to me. I've loaned this out to a couple of groups, and I found my meter back there on the table. So you need to bring it back to me, and if you accidentally carried my meter leads with your meter lead, you need to give them back to me. So here I increase the speed, and the output of my generator does what? And I come down and decrease the speed. Now, to get this, we would have to know the volts per RPM. So right now, I guess I could turn it down real low, and then I could count it, and I could use that to get my transfer function, but it would be hard because it's varying that thing. So there's all there is to a DC tag. But somehow we would still have to convert this into a watt, into a speed, right? Everybody understand that? So we'd still have to bring this into some type of analog to digital converter. So this is my motor on this side, and this is my motor I'm running as a generator on the side. So DC tags, pretty easy to understand. These guys here have a really, really linear output. They're very precise. The only problem we have with DC generators is that they have to have that commutator on them, right? Y'all understand that? Yes or no? Yes? Everybody okay? Yeah, well, DC motor, even though DC motors work off a current, basically they have so much opposition in them. So if we increase the voltage to them, we increase the current, we increase the magnetic field, and the motor speeds up. So DC motors are voltage control devices. So as we increase the voltage on the armature, the motor speeds up. If you decrease it, it slows down. So it's very, very reliable, very understood technology. The only problem we have with DC motors is that we've got to constantly change one of the magnetic fields to keep the motor doing what? Spinning. So what we do is we pass current into the armature, which is the rotor. A lot of people call it the rotor, but that's technically that's the name for an AC, the part that rotates on an AC motor. But you understand when people call it rotor, you know what they mean. So the rotor, we have this slotted thing on it. We call it a commutator. That's basically constantly keeping the magnetic field 90 degrees out of phase with the motor. And what we do, so as it spins, what we do is we constantly switch it. So if this is a north, this is a south, this would be a south, this would be a north, then the motor would spin. Well, what we do now is we switch it. We keep switching it so they're always 90 degrees out, right? Does that make sense? It makes the motor spin. I got a really good video where the guy shows it. So we transfer power into the rotor through a commutator, which automatically, that means we got problems because we come into there with brushes. So let me pause the recording. No, I can't. I can do it this way. So this has got an AC tack in it, and also it's got the motor in there. The AC tack is the two yellow wires, and then the motor is the blue and red wire. What I'm gonna do is I'm gonna move my power supply over to that guy. The polarity on a DC motor determines the direction they'll run. That is. So this is an AC tack. By the way, we're looking at the scan rate. In fact, you can see this on my monitor. The way it looks like it's. What we got is we got this camera taking pictures and my display sending pictures, and they're not in exact sync with each other. So this is not flashing like this, guys. It's just the scan rate of the scope. So I'm going to increase the speed, and notice two things happen. Not only does the frequency go up, but also the amplitude goes up. So this is an AC tag. So what is that? I could take this, I could rectify it. If I needed DC, I could rectify it. So what advantage does the AC tag have over the DC tag? No commutator. We got a magnet and we're spinning a coil. That's all we're doing. We're spinning a magnet inside that coil. So there's no commutators on this, right? You understand that. So these guys would last a lot longer. If I needed DC, I could rectify that. If you take solid state, you'll learn how we do that. But that's what your car has. So your car has a rectifier assembly. So we have an alternator, but our car runs off DC, right? You understand that? So inside that, we have what we call a rectifier, and that's electronic devices that take AC and convert them into what? Into DC for us. They're diodes is what they are. So the purpose of rectifier. So I could use the amplitude or I could use the frequency. So this was actually set the speed on a 5 1/4 inch floppy disk. This was the actual motor that came off that thing. And so what happened is the electronics would read that voltage and make sure the disk run at the same speed, right? You understand that? In fact, we could calibrate it. I need to go see if I can find one over there. We used to teach how to calibrate it back when they were very, very popular. How to take them apart and put them back together and calibrate the speed and everything else. So that's an AC tag. Pretty simple to understand. You okay there? So an AC tag gives us two things that would give us speed. We can have a circuit that checks frequency. That's the rate of the pulses. Or we could measure the voltage to get the speed, depending on what system we're using. Are you okay? Questions? Pretty straightforward. So DC tacks, tachometers, most people just call them tacks. And this is it, guys. So this guy gives us a linear voltage depending on speed. Both of them do. So these are very, very accurate, as far as checking speed. Are we okay? An AC tach generator feeding a computer. So we have to run through an ADD converter. The ADD converter would give us a binary number that represented the voltage. We wanted to run this into a computer. ADD is analog to digital converter. Most of your PLCs, most of your program computers have these in them. Used to, we'd have to do it external, but every PLC since the Micrologic 1100, it has two analog input only. The the compact logics we have, I'm not sure how many go back to it. So this is even coming very, very popular on program controllers, because a lot of our sensors are analog sensors. Anybody had Intro Robotics? How many sensors on the Lego robot were analog? The ultrasonic sensor was analog. The light sensor was analog, right? You understand that? The touch sensor, that was digital. And then the servo motors, they used incremental encoders. So the servo motors that ran the robot used incremental encoders. So this is the way the one in the, it was just a rectifier. This is the way the circuit ran inside the 5-4-inch floppy drive. We fed it into an F to D converter, frequency to voltage converter, and then it used an output voltage like a DC cache. So the advantage of an AC cache is it doesn't have that commutator, right? Understand? It doesn't have separating. So these guys will last a heck of a lot longer. No preventive maintenance required unless they get goofed up, Well, I'm not saying there's none, but a lot less preventive maintenance. Incremental encoders, we already know this is on the test. So an incremental encoder we can use for 3 different things. Different types. Just a straight incremental controller, we could use it to check position and speed. Check direction, we have to have what they call a quadrature incremental encoder, which gives us 2 different pulses. So that would be the big difference. So I guess I need to put a note up here. So this is basically an incremental encoder. So to get speed, we'd have to do a little math. So what we would do, we got several ones. So RPM, this is probably what we do, is we take the time. So what we're going to do is we have to know the time between the pulse. The time between the pulse. Then we multiply that times the watt. Number of T. And then we multiply that times 60. Makes sense? We're dividing. Well, how many T's does this thing have? It's got 15 T's. I didn't use it. So these we would have to do a little math to calculate. So this is a single channel incremental encoder. In fact, this is actually the encoder that's on this print. So here's an incremental encoder right here. And this is used to sense the position of the paper. This is an incremental encoder right here. You can't even see the lines. This is a linear incremental encoder right here. This is what the printer electronics use to sense where the print positions are at, right? So that's right here. So this guy right here, this printer here has at least 2 on it. So it's got this guy right here that's used to sense the position of the paper, to know where to print at. And it's got this one right here to know where the actual print positions are at. cool the way these jet printers work. So it's got little, they're piezoelectric, but they work just the same as water gun. And then we squirt the ink out, and then it actually combines when it's in the air to form the different colors. You do dots, so everything you do on a printer is done in dots. You can laser print. It's just a dot. You get from 5 dot 7 dot. So you can the dots are actually merged. So don't get a chance, I'll come up with these actual components that are actually being used to design. Okay, guys, let's take a 10-minute break. So this is what's on the actual printer up here. It's got the single channel ADD converter, incremental encoder. These are becoming more and more popular. If you don't need to sense direction, if all you need to sense position and speed, then of course just a standard single channel incremental encoder will be fine. If you need to sense direction, then we have to use what we call a quadrature incremental encoder. The first robot that we ever got was a Rhino robot. And you could actually see the quadrature encoders. It was really, really neat. I'll see if I can find one, because it's real good. I use photoelectrics just like most of them do. The one we have uses Holophane. But what we do is we have two sensors that sense the slot or sense the magnetic field. And they are spaced so they give out pulses at our 90 degrees up phase. And we have two channels, referred to as A and B. I can't remember which one it is. I think A means clockwise rotation. If A leads, I think it means what? Don't quote me on this. But I think if A leads, it's a clockwise rotation. If B leads, it's a counterclockwise rotation coming out of the encoder. So that won't be on the test because I don't, unfortunately. So right now, this is A and B. Notice that A leads B by 90 degrees. And then if we swapped it, then the other one, it would change, right? You understand what I'm saying?
I'm trying to read that right now. What's that say? Waveform?
This waveform shaping circuit. So what they're saying is that the pulses that we get out, it's not perfect square waves, so we run it through an electronic circuit to actually shape it. So if you look at so here's our quadrature encoder is on the back, so the quadrature encoder is back here. And then of course we have the DC motor here, and then we have a gearbox. So what we're doing is we're looking at the speed out here, plus 131.25 to 1 ratio. So that means our DC motor has to turn 131 and a quarter turns to make this output shaft turn 1 turn. So this guy's turning really slow. You can hear the motor turning pretty fast. This guy right here turning really slow. Well, even though we're getting the actual encoder itself is 16 pulses per revolution, but on our output shaft we have to have 131.25 revolutions of this. So what our output shaft sees, it sees 2100 revolutions pulses per revolution of the output shaft. Because motor power is 12 volts. I think we got these off the General Electronics. The encoder can run off anything between 3.5 and 20 volts. PLC might be able to pick this up. I need to check. In fact, this is becoming. These guys are coming more and more popular. The new PLCs that we got, the Contact Logic 24 LED PLC, actually has it has this input. It's got A and B input for the quadrature encoder. If we just use one input like the A, that would be for a single channel. But if we use a quadrature encoder, then we use AB. And I need to do a little more research on those to see if it actually will give you the direction of rotation since it's set up for these quadrature encoders. Right now, we're just looking at, but we could set up a circuit. So we've got a quadrature encoder. So what we can do is we could actually set up a counter that counts both these rising edges or positive going edges. Well, if I did that, then instead of getting 2,100 pulses per revolution, I would get 4,200 pulses per revolution, which means now my speed would be more precise and my positioning would be more precise, right? You understand that? If we counted the bottom, if we counted the rising and the falling edges, if we could do that, then that's going to be 2,100 times 4. So that would give us 8,400 pulses per revolution. If we set up a circuit that had the ability to count all those edges. And if you get into digital, edge-triggered circuits are not that complicated to have. Now, whether our PLC will do this or not, I don't know. I wish I could tell you, but I haven't had a chance to play around with them. They're still relatively new. I just know that they will take quadrature encoders directly into input. So it's got two inputs for A. And if y'all remind me when we're doing 196, I'll show y'all those inputs for these quadrature encoders and also the analog encoders also. So most of your programmable logic controllers now actually have analog inputs because we have a lot of analog sensors out there, right? You understand that? Especially if you're in an environment where you gotta keep a constant temperature and stuff like that. And a lot of them now are actually supporting quadrature encoders, or you can buy a module that supports quadrature encoders. So here's our encoder. So what we have is this is probably you can go ahead and do all the math. So you can take 1/2100 and then you can multiply that by 60. It comes and gives you that magic number right there. So if I was programming a PLC, I wouldn't do the math. I would just use that number right there. I would say, how many pulses do I get per revolution? This is going to be in seconds, by the way, and not revolutions per minute. So this is going to be in seconds, and then these are pulses per second. And that's why we have to multiply it by 60 to convert it into pulses per minute, right? Which would give us our revolution. So most of them, you take the number of pulses, you multiply it by 60. You take the reciprocal of that, multiply it by 60, and then this would be the actual formula you use in your PLC. You wouldn't go through that stuff up there. Or we could do this one. This is the one. This is the one that we'll use right here. And by the way, this is actually on the Siemens Level 1 test. This question that we'll look at that will be on the next test. But I'm going to give you, on our test, I actually give you the formula. So first of all, we need to know time. And that's one thing nice about an oscilloscope. An oscilloscope measures time for you. And I'll make this even so it'll be a little easier. I think I went too far. So, since this is a 9-3, I've got my stuff all taped up, so my hard on front of this, so the hard on the swap. we'll do is we'll look at the chart. Okay, so I'm going to start with so because it limits the number of rounds. So it's, so I would come up here and count. So far, I had that. So this is where it starts. So I have 1, 2, 3, 4, 5, 6, 7. Oh, it's over here on the side. Each one of these is counted. Two 200 microseconds per division times 8. That would give me what? 8.6 milliseconds, right? Right. Or 1.1. So it's times 8, so it'd be 1.6 milliseconds. I don't know where I get 1.6 milliseconds. So that's one pulse. But I get 2100 pulses per revolution. We're measuring the time for one pulse. That's not good. We're measuring the time for one pulse. We need to people that figure that right. 1.2, I'm sorry, times 8, 1.6 milliseconds. Okay, so what do I need to do next? By the number of pulses we get per revolution, right? Which would be 2100 on ours. So that'd be 1.6 milli times 2100. And when you get through with that, you need to do what? Take the reciprocal of that. That turns time into rate, but it's still going to be revolutions per second. We want to turn it into revolutions per minute, right? So then we multiply it by 60. So how fast is my motor running? So I take 1.6 milli. I would multiply that times what? I'd multiply that times 2100. Is that okay? And then I would do what? Then I would take the reciprocal of that. Everybody's got that key. On your, if you got a scientific calculator, it's either going to be x, 1 over x, or it's going to be x to the minus 1. When you raise the number to the minus 1 power, it takes the reciprocal of it. Y'all never figured that out yet. Or if it does have the 1 over x. And we use this formula so much in electronics because it gives us the opposite, right? So it gives me, I can go to time to rate. So then I multiply by 60, and that will give me my in revolutions per minute. This is universal, by the way. Revolutions per minute. This is international. We do change things, when we go, metric and just customary. So this is international. Greatest speed of revolutions per minute. Well, no matter where I was at, we would probably be doing the same thing. So what's our speed? Anybody got it yet? Revolutions per minute? It's gonna be kind of hard to map out. Everybody get that? So I'll work it up here. Let me bring up my calculator. So I got my scientific calculator up. It's a 1.6 times 10 to the negative third times 2100 equals that reciprocal times 60. About 18 revolutions per minute. So let's see how accurate you are. So it's going to be around 18. So we'll come over here and bring our camera back up. Anybody got a stopwatch? Everybody got stopwatches, man. Y'all tell me when to go, or I'll tell you now, and you can start your stopwatch. And we'll count the revolutions. So we'll count them right about there. So somebody get their stopwatch out and tell me when I say go. Everybody got it out? Okay, we'll count it right here. Ready, set, go. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Pretty good, right? So a little bit of math, we could program this very easily in a PLC. And like I said, the new PLC that we have actually supports quadrature encoders. So this is just a different variation of an incremental encoder. So which ones did we talk about? So we looked at tax, right? We looked at variable reluctance, which is still very popular because it's got very little moving parts. It's not electronic. What you sense it would be electronic, but the sensor itself is very fundamental, very reliable, very rugged. And like I said, it wouldn't surprise me if I'm almost sure this is used on most anti-lock brake systems. As far as sensing the speed of your car, that's what I say. All you'd have to do is have one of these things down inside your transmission looking at one of your gears. So variable reluctance, we look at Hall effect, which basically works on the same principle, but this is totally electronic. Then DC tax, these guys give us a DC voltage that is proportional to speed or velocity. The only problem is they use commutators, they use those brushes, and eventually they'll do what? They'll wear out. Then we have our AC tax. These work on basically the same principle, but they don't have brushes and they don't have commutators in there. So these would be, so that's DC, guys. But we're still going to have to convert it over so our system can recognize this. I don't know of very many analog inputs that will give us a frequency, but we could very, very easily convert this over to voltage. I could use a diode and a very, very small capacitor. And that's all it would take to go from a frequency to a voltage. Then we looked at incremental encoders. So incremental encoders, it would be hard to get speed of an absolute encoder because it's got all those different pulses, right? You understand? You might have looked at use a zero channel or channel first channel to get speed. But these guys are really easy to get speed. Just the rate of the pulses. The rate of the pulses gives us the speed of the device. Not much math involved. A single channel, like I said, that's what this guy uses. And then, of course, the quadrature encoder, which gives us two signals, an A signal and a B signal. And they're always 9 degrees out of phase. Which one leads depends on the direction of rotation. So if A leads B, it would be rotating one direction. If B leads A, then it would be in another direction, it'd be in the opposite direction. So these guys, we can get speed off of them, we can get position, and we can also get direction. So, like I said, the first robot we ever had, motors were actually, by the way, servo motor. A servo motor is a motor that provides feedback. The feedback is built into the motor. So if you hear that term, servo motors, that means it's what? It's built into the motor. Some of them you can't change out. You can't change the motors out on. The big old fat robots over there on 107, those are designed, those motors are so expensive that you can pop the back cover off and you can change the encoder. But if you got into like the smaller robots, like the Fanuc robots, the encoders are inside the motor just like this guy is. So if your encoder went out on one of those, you'd have to change the watch. You'd have to change those motors, those servo motors. And of course, then you'd have to reestablish these motors. So that's it. That's all I know of that actually sits as speed. We can use ultrasonics. I don't know why that's not in. Sit out of the hole, all the sides, and sit out of the hole, calculate how much most of them now you can break them. You break ours, that hole, I don't know a lot of time. I can't remember the last time I saw them. Luckily, they don't have enough place to do all that. They don't have time to do that anymore. They're too busy handling domestic disturbances, right? So we could use light. Probably need to add that. We could use laser beams. We could use ultrasonics to sense speed. But these are the ones that I've run into more. I've never seen that used in industry. I've seen TAC generators used a lot. I've seen, and now incremental encoders, because it's already digital. Incremental encoders are already digital, so that means we can bring these encoders into a programmable controller, and we don't have to convert it over to digital, right? You understand? Because the inside of a PLC is nothing but computers, which deals with computers don't deal very well with analog. They deal nice. They love digital, so they don't have to convert it over to something. So any questions?